All right, so we are back on it at this point. Let me make sure I get my slideshow working here again. There we go. CSTN 283, March 29th. And this is actually the Learning Unit 8. That's the Weatherization Basics. We've gone through a lot of this on our site visit. Just a quick update on the project. And we've got all of the group field reps who are going to do another site visit, and that's scheduled for Friday, 11:15. So before we break, you guys will have another chance to get in the house. Hopefully your groups, I know some of you are further ahead than others, but hopefully you've started on your list and you've got some things you want to check out. We'll be able to get into the attic. You'll be able to take additional measurements. And if there's anything that we go over today, you might want to add into your program. A couple other things I want to stress too on the project, and what I think is more important is that you guys come together and you put your effort forth and put together a reasonable weatherization plan. There really isn't a right or a wrong answer to it. We discussed this while we were on the site that day, and you know there are a lot of different strategies and approaches that you can employ, and some of them may or may not be more effective than others, and a lot of them there's really no exact way to be able to tell. You can make some good estimated judgments, but there's really no way to say, okay, right now we're getting 2,590 CFMs on our blower door reading. If we seal the basement window, we're going to take that down to 2462. It's just, we can make a judgment that it's going to reduce the airflow, but it's not as exact as we would want it to be. So again, I talked to a few of you and kind of worried about what was right and what was wrong, and there is no right or wrong answer. The point is to really think about what you can do and put together an effective plan. Any other questions on the assignment, what it entails, what you're supposed to do? So we'll revisit it again at the end. If you have any questions, let me know. And then hopefully our goal is when you get back from break, we're looking at, I think it's the following week we have it on the schedule to have the plans turned in and completed. 15th? Yeah, I think it's when you get back. So we'll go over them, evaluate them, and then we'll kind of come up with our own plan. I'm sure that I already know, just because I'm working with a couple of the groups, that some of you have got some things on your list that other people didn't pick up on, and vice versa. And so we may take some of the best out of each plan and put it together in what we actually execute on site, and then you'll all be able to do your final blower door test. So, but let's move through really quickly on this, and why the whole point of what we're talking about, and why we're trying to understand how and why buildings lose energy and how to fix it. You know, this little graphic I think is very telling, and if you look at the little pie chart on the left-hand side, we spend a lot of time talking about new construction and how we can get new construction to be as efficient as possible. We've got building codes that enforce minimum energy requirements, and the new housing stock is fairly energy efficient. But you can see that tiny little gray sliver is actually what the new housing stock is. It's a very, very small part of all the houses that we have out there and the buildings that we have out there. And that existing housing stock is, for the most part, unless it was built in the last 10 years, on a whole pretty inefficient. So it's important because it improves the existing building stock. It also doesn't consume any more ground. It uses less materials. It's a much more sustainable way of building and reducing our energy footprint. So challenges are not each building is the same. And this is both from a weatherization energy efficiency standpoint and an overall construction standpoint. The beauty of new construction is you are working from a clean slate every time. You're starting from ground zero, so you can influence the energy performance, the design. You've got a lot of tools at your disposal because you haven't done anything yet. When you go into an existing building, you work with what you've got. And it can range from fair to Midland and worse on most existing buildings. And so there is not necessarily, we'll talk about kind of a basic energy audit and a pathway, but there really is not an exact science to it all. Lagan talked a little bit about it, and you can certainly start to predict where your air leakage and your energy loss is going to be, and most of the time those predictions are right, but you just never know until you actually get in there and start working on the systems. Kind of just, we're going to focus on the second part of this, but a lot of what happens, a lot of energy professionals are called in usually when a building's going to go through some sort of renovation and remodel. Before you start working on any of the energy improvements, it's always a good idea to make sure that there aren't any structural deficiencies. Certainly anything that was built before 1978 has the potential for lead paint. So that's something to look at before you start going in and pulling things out, whether it's in the name of adding insulation or air sealing. Make sure you're not dealing with lead or asbestos, any other hazardous materials. So again, evaluating the structural condition and not just looking at whether the building is standing up, but do you have moisture issues, intrusions in the roof or walls? Can you see any water damage or water spots in there? From a sustainability standpoint, is there anything, if you are going for the remodel part of it, can you use any materials? What will you need to replace? And again, are there any indications of structural damage? If you are doing any type of weatherization, energy auditing, you're going to find yourself in the basements and the attics and the crawl spaces of houses, and that's normally where most people don't go. And it's also normally where most of your structural deficiencies are going to become apparent first. So oftentimes as the energy auditor will go in, a homeowner wants to spruce up their house a little bit and make it a little more energy efficiency, and they come to find out that they've got black mold and standing water in their crawl space. Obviously the first thing they want to do is not to start caulking up their rim joist. It's probably address those issues. So this is just a basic home energy audit checklist, and this isn't necessarily the path that you have to follow, but it gives you kind of an idea of what it encompasses. And it could start with trying to, as part of determining what the baseline is of that house and what the energy goals are going to be, looking at the past fuel consumption. If you can get the energy bills for the past 6 months or the past year, so you can get a total demand load on the house. Find out what any of the problems might be, talk to the homeowner. Are there places in the house that are cold, that are drafty? Are they having any moisture issues anywhere? Then the basic audit procedures, and this is going to vary depending on how extensive the plan for the audit is. But visual inspection, blower door testing, a big part of the energy audit also, I said with the structural issues, but also with safety concerns. We didn't talk too much about combustion appliance test, a minimum depressurization CAS test. I know that Lagan touched on it with some of you when we were in the basement, but when we're talking about combustion appliances, the furnace, the hot water heater, anything that's burning natural gas or fuel oil, and especially in older houses with older equipment, it's not a sealed combustion unit. It's actually using air from in the house, and so the flue where the gases escape is open, and it has the potential to backdraft. So making sure that the equipment is properly vented. We'll talk a little bit when we're going to talk about duct leakage testing, and we'll talk about the CAS test, but combustion area zone test, and that is where, and you can use your blower door to help with this, but you can actually test to see if you're getting enough natural draft out of those appliances so that even in the worst case scenario, and that's also another name for the combustion appliance zone test, is the worst case depressurization. So you test it so that even in the worst case scenario, you're getting enough draft that carbon monoxide and the flue gases are still exhausting out of it. We don't go too deep into it in this class, but just knowing and understand what it is. And then the last part of it really is taking what you find in that audit, and depending on what level of testing you do, putting that together in a weatherization plan and a recipe for upgrades. So we talked a lot about the blower door. We have and just another quick note, all of those videos that we took from the site visit are accessible via Dropbox. They're too long for Moodle. They wouldn't upload onto Moodle. So did you all get the email about those videos? Okay, good. If for some reason you can't get them to load, I mean, if you're just dying to watch them again because the experience wasn't enough, you can't get them to load, let me know. But you should have a pretty good understanding of the blower door, the basics of the operation, how it works, and what it does. And again, we're going to do just this. We've tested in. We know the stage of the house currently, and then once we do all of our work, we will test out, and so we'll be able to measure our results to some degree. The other part of the blower door, and this is in relation to older houses, and one thing that you definitely want to understand and be careful of, you can certainly go into an older house and it may have enough natural air leakage because it's got old windows and no caulking and no weather sealing. It's got enough natural leakage that it's getting proper ventilation. But you can certainly go in and tighten it up to the point where you can create a negative situation where you're not getting enough fresh air in and not just getting stale air, but you're getting the rest of the volatile organic compounds, the VOCs that are building up, not getting enough moisture control. And so one of the biggest things in a lot of deep energy retrofits is to understand the ventilation requirements. And so based on what you're testing, you can get what's called the minimum ventilation requirements, the minimum ventilation guidelines. And so I won't ask you to run all of these out, but I would ask you to understand what these mean. And two different ways that can normally be figured, and that's based on the actual testing, and that's the air change per hour formula. The second is the basic square footage formula. And so what this is what the minimum ventilation guidelines do is give you, based on what you're estimating the tightness of the house is, or you're testing the tightness of the house, do you have enough fresh air ventilation, or are you going to be required to bring in mechanical fresh air? So the square footage formula, what I'll start with, is just based on the number of bedrooms and the overall square footage of the house. And so you can look at, they start with a 7.5 CFM per bedroom plus 1. So if you have 2 bedrooms, you'll start with a 7.5 plus 3. This one is a 3-bedroom example, so 3 bedrooms plus 1. So So 7.5 cubic feet per minute per bedroom plus 1, and then your total square footage times 0.01, and that gives you a target cubic feet per minute of minimum ventilation. The second one is based on the actual volume and the actual air changes per hour, and it's going to give you a little bit more, usually a little bit larger number, but a more accurate number of the ventilation that you should have. And so the minimum ventilation guideline is 0.35 air change per hour times the volume divided by 60, because we're looking at cubic feet per minute, and air changes per hour. But one of the things that you'll notice, the 0.35 air change per hour, would you assume going into an older house that if you were doing a blower door test you would get 0.35 air changes per hour at pressure? No, because that's actually not air changes per hour at pressure. That's natural air changes per hour. And I know what you're thinking is, why can't they keep all the formulas in air change per hour at 50 pascals? And that's a question that no one has really truly answered. But fortunately, you can convert it, and natural air changes per hour is a little bit more difficult to convert. It's not, when you run a blower door, you're creating an artificial situation that doesn't happen, and it doesn't exactly transfer. It's not a 10-to-1 or 8-to-1 ratio. It is based on your actual blower door rate, the volume of the house, and the N factor. And you probably, have you read about the N factor? It's in your book. And I won't, anytime we do a calculation for a blower door, everything's going to be at ACH 50. Every time I write it, I'll write it just as it is here with ACH NAT for air changes natural. But you will see it used both ways, and you'll need to understand the difference. But the N factor is just a basic correction factor, and it's a way to try to take into account the exposure of houses, one-story or two-story. They're all going to have slightly different performance factors. Depending on which climate zone you're in and how many stories your house is, what kind of exposure it has, it'll range anywhere from 9.8 to 29.4. Typically averages about 20 for most climate zones, 2 through 5. So for this example, question?
Yeah, can you go back to the minimum ventilation guidelines? So that 0.35 ACH in the first one, that's natural? That's natural. So that's not doing the blower door?
That's not the blower door. That's just natural atmospheric pressure.
Okay, so you hook up the blower door and not turn it on, and that?
No, this is just a guideline. Okay. So this, what this tells you is that at 0.35 natural air changes per hour, using the volume of the house divided by 60 will give you your target ventilation rate. Okay. And if you fall below that target ventilation rate, you should have some type of fresh air, mechanical fresh air intake.
So that's just a generic average?
This is just, this is just a standard. This isn't, what's that? I can't hear you.
Yeah, there's always that.
Yeah, this is just so if you're going, when you use this, if you're the energy auditor and you're going into a house, and you're going to do a blower door test, and then do a whole bunch of improvements, you want to make sure that you don't get it too tight. So when you test out, you're gonna have this minimum ventilation that you've got to have in the house that should be happening all the time.
So, so the example shows like 93.3, so when you do all your changes, you test out, you want to make sure you're at 93.3 CFM for your ventilation?
At natural, yeah,
Yes.
not at pressure, yeah. So inversely, you can take your, what you'll find, you'll see a lot of the programs that you can use will actually convert this for you with your blower door. I'm sure that if you saw the app that Lagan was using, I'm sure that would convert pretty quickly between natural and that 50 pascals. Or you can just figure it before you go in and understand that, back to this one, you can use this same formula when you get your target, and you know your end factor. You can use this formula to get what your air change per hour at pressure is going to be. And I try to focus on what we've been talking about and what we've been working on with ACH at pressure. I just think it's important to know this because you'll hear this thrown out there and you'll hear people talk about, we're talking about houses that are at 3.0 air changes per hour for code. Getting down to 2 is pretty tight. 0.6 for passive house, and then you'll hear people talking about 0.25, 0.15. And occasionally you'll talk to some people that are uninformed and you'll tell them that, yeah, we ran a blower door test and we got 2 air changes per hour, and they'll say, oh, that's nothing, I got 0.25, I'm way better than that. When in actuality they were at about 7. So
At least they weren't breaking the law.
they weren't breaking the law. So yeah, so anyhow, that difference between natural and air changes per hour at pressure, and unfortunately I'd like to tell you that it's just 10-to-1 or 12-to-1 or 8-to-1, but it's not. Figuring natural air changes per hour is a little bit trickier, which is probably why everybody does at pressure. So it's a little more absolute. So this, we got a halfway decent opportunity to do this on our own in the house, and so if you're running these tests, where do you find the leaks? The thermal imagery is a great way to do it, and I'll bring it back again for our site visit, so you guys can have it. You may want it when you're in the attic. Even without the blower door running, if you've got enough of a delta T and it doesn't take more than about 10 degrees, you can really find a lot of significant spots.
Would we be able to take pictures?
Yeah. Yeah, and you know what we can do, if you want to, we didn't do it at our site visit, but we can actually take pictures right with the thermal imagery camera when you're up there, and we can download those, and I can ship them out to your groups, so you can have those. But again, a couple other conditions, and these are pretty dramatic. I don't think we found anything out of the ordinary crazy when we were using the thermal imagery camera, but just standard stuff, thermal bridging and some other places where air was leaking in.
That's pretty bad.
Yeah, that's not good. There's no air sealing, and it looks like the insulation was fairly incomplete, and it's actually completely missing in a couple of these bays. So what we'll run through now, and most all of this is in that Energy Out West field guide. If you guys have not downloaded that and started looking at that for your group project, I highly recommend you do it yesterday. Concentrate on sections 4 and 5, which is going to be the lighting, the appliances, and the envelope stuff. don't worry so much about, obviously, given our budget, our $500 budget for our project, we're not going to be swapping out equipment, we're changing windows. So really focus on those things where we can actually make.
We're changing furnaces.
We will not be changing the furnace, no. I think that was still an 80% efficient furnace in there.
What's that under? You said down low.
The Energy Out West Field Guide, it's on Moodle.
Yeah.
The link to it's on Moodle. But yeah, basically what this last section that we're going to go through is, maybe I ought to cut this in half right here. Yeah, let's cut this in half real quick, and then I'll start right back up again with another recording.